Today we're going to look at exponential growth and decay, and we'll look at that with multiple representations. So with the warm-up, what is 2 to the 5th? Well, in our calculator we can type that in. We can do 2 to the power of 5, and we get 32. Our expanded form is basically, what does that mean? And it means you take 2 and you multiply it by itself 5 times, and we get 32. So expanded form is writing it out. The base is 2. The exponent is 5. So we write the base 2 5 times. All right, let's take a look at this in multiple representations. We're going to take a look at this one problem. One cell divides into 2 every day. And we are going to write a table for it. We're going to graph it. And we'll write the equation. So if we take a look at the first one, that day is 0. Again, we start with 1 cell. So in expanded form, if I write that out, that's just a 1. Day 1, it doubles. 1 times 2 is 2. And if we write that in expanded form, it's 1 times 2. All right, on day 2, again, we double it. So on day 2, there are 4 cells. And if we write it in expanded form, it'll be 1 times 2 after day 1 times another 2. The next one at day 3, we'll have 8 cells. Again, we're doubling. So again, we take our 1 cell and we multiply by 2 for day 1, for day 2, and day 3. Day 4, we'll have 16 cells, and day 5, we'll have 32. And for both those, remember we started with the 1 cell first. And at day 4, we've doubled it for 4 days. And day 5, we doubled it for 5 days. So for n days, to figure out the number of cells, we can write this equation. Y equals, we started with 1 cell, and then we double it every day. So there's the equation. Start with 1 cell and we double it every day. If we graph it, here's what it looks like. Day 0, we have 1, 2, 4, 8, 16, 32. And so if we graph it, here's what it would look like. And that is an example of exponential growth. So again, we've looked at 3 models here with the same problem, taking 1 cell and dividing it every day. We have a table, an equation, and a graph. So now let's take a look at the different parts of the equation and what they have to do with the equation itself. So with the first one, I want you to graph on a graphing calculator 2 times 2 to the x, 3 times 2 to the x, 4 times 2 to the x, and then make a prediction. What do you think will happen when we have 5 times 2 to the x? All right, so I'm going to open a graph page. All right, so the first one's 2 times 2 to the x. Okay, so there's the original. Hit tab and we'll type in the next one. Let's do 3 times 2 to the x. Let's do 4 times 2 to the x. So take a look at what the 2, the 3, and the 4 are doing, and if you'll notice, here's the 4 right here. Whoops, I erased it. It would be the starting value. The y-intercept is at 2 here, at 3 for this one, and at 4 for this one. So if you make a prediction, the 5 would be like the starting value of the y-intercept of the new graph. So 5 would be the starting value of the y-intercept. And if you think about what this means, it means, like, let's say you start with 5 cells and they double every day. So for all of these, they're all doubling, but we start with a different amount of cells each time. All right, let's take a look at what if we keep the first number the same, which we know is the starting value, but we change the second number. What happens to the graph? Okay, so let's do that. I'll just open a new graph page. It's easier than clearing. All right, so we start with the same one. 2 times 2 to the x. Okay, so we know that that starts at 2 and it doubles every x. All right, let's do tab and let's do 2 times 3 to the x. You can see it still starts at the same value 2, but now it's steeper. And if you think about what that means, it's like starting with 2 cells and tripling them every day or every hour. All right, let's do the next one. 2 times 4 to the x. Again, it goes through 2, but it's even steeper because if you think about it, it's quadrupling every day instead of tripling or doubling. So if we take a look at that, the 5 is going to make it more steep because it'd be like multiplying by 5 every day or every hour, whatever x would stand for. So this is going to make it steeper. And they all go through the point 0,2 because they all start, it's not 0,2, I'm sorry, it's 2, 0. Because they all start at that one point at time 0. All right, so anatomy of an exponent, we have the a, which is the starting value. The b is the base of the exponent, so b has the exponents, the base. And it's going to be either growth or decay rate. We've just looked at growth so far. And then x is time. So we've looked at x being days, but it can also be hours or minutes or seconds or any unit of time. Okay, so question. What is the a value for the following function y equals 2 to the x? And so we see what the base is. The base is that 2, the growth rate of 2, doubling every time. So if you don't see a number in front, there is an invisible 1 there. So here a is 1. So here the starting value is 1. It's like the original problem. We start with 1 cell and double it every day. And that's what it would look like. Okay, so then next part, open a new graph page, and can you graph the following? What happens if we have 0.25x, 0.5x, and 0.75x? So let's do that. Let's do what was the first one? 0.25x. So here the starting value is 1, and then we have this rate of 0.25. And we can see that instead of growth, it's decay. Let's do the next one, 0.5x. Make a prediction on what's going to happen to your graph. You can see it's decaying faster. And our last one, 0.75 should decay even faster is my prediction. Right here. And you can see that it's decay as well. Okay, so let's summarize that right here. How can you tell if something is growth versus decay? So decay, growth is when your a, your starting value, when the absolute value of that is greater than 1. So you take a look at it. If it's greater than 1, this will be growth. If the absolute value of a is between 0 and 1, it will be decay. So like 0.5, all of these were decay right here because they're between 0 and 1. And then from the functions unit, what do you think the negative will do? We know the first graph looks like this. And so if there's a negative, what will that look like? And if we graph it, it goes the other way. It's a reflection over the x. So this exponential function follows the same rules as the other functions did last chapter, just the equation looks different, so reflection over the x. Okay. So some examples. Which of the following functions show growth and which show decay? So I'm going to write a few things. I'm going to write the starting value, and then I'm going to write the growth or decay rate b. Remember, they're all in the form y equals a times b to the x. So if b is 3, 3 is bigger than 1, this will be growth. Okay, the next one, the starting value, we're going to start with 100. But this is going to be decay. It's like dividing by 4 every time or multiplying by 1/4. So b will be 0.25. It's decreasing every time. So this is decay. And then our last one, the A value is 12. We start with 12. But then if we go inside this right here and actually figure out that number, that is 0.9. And that is less than 1, so that will be decay. We take 90% of the time before, and that's going to decrease by 10% every time. A scientist has discovered a new strain of bacteria. The bacteria initially contained 1,000 bacteria, and it doubles every half hour. So if we double this, we will get 4,000, 8,000, 16,000, 32, I'll put K, 64K, 128K, 256K. So we're doubling it every hour. Oops, I can't write the K there. There. All right, so write the function. So with the function, we need a starting value. So times 0, that's 1,000. And it's doubling, so that's our growth rate is doubling every half hour. Oops. Okay, so it says determine how many bacteria are present after 24 hours. So what you have to figure out is for X, how many half hours in 24 hours. And that would be 48. So when we type this in our calculator, it'll be 1,000 times 2 to the power of 48, which is some big number. We can see it's already at 5 hours, like 256K. So we type it in. So we would type in 1,000 2 to the power of 48. It's a really big number here. So I'll just leave this answer. Okay, so you can see it increases quickly. All right, on the next one. The half-life of a radioactive kind of cesium is 13 days. How much will be left after 39 days if you start with 96 grams of it? All right, let's write the function. Why we start with 96, it's half-life, so we're taking half every time. And X is how many 13s are there in 39 days? So we divide. 39 divided by 13, there's 3. So 13 goes into 39 3 times, and that is what X is. So in our calculator, we'll type in 96 times 0.5 to the third power, because it splits in half every 13 days, and there's 3 of those in 39 days. All right, type it in. 96 times 0.5 to the power of 3, and that would be 12. 12 grams. Whoops. All right, so there's our answer, 12 grams. All right, the next one, there's a population of 48,000 bacteria in a colony. If the number of bacteria doubles every 202 hours, what will the population be 808 hours from now? Starting value 48,500. It's doubling every 202 hours. So you have to figure out for X how many 202s are in 808. So we'll take 808, divide by 202, and we'll get 4. So it's going to double 4 times within that amount of time. So you'll type this in and get the answer, which I won't do. And the last one, in 2000, there were 120 squirrels in Central Park. The population increases by 6% each year for 10 years. If this pattern continues, how many squirrels are in Central Park this year? All right, so we start with 120. Now it's increasing, so our number has to be bigger than 1. So it's going to be 1 plus, we're going to change our 6% to a decimal. If you divide 6 by 100, you get 0.06. So those would be 1 plus 0.06. All right, so what the 1 stands for is we take the 120 squirrels from, it's 100% of the squirrels from the year before, and to that we add 6%. And that's why it's 1 plus, because we want our population to increase, not decrease. So you have y equals 120 times 1.06. It's been 19 years this year since 2000, and you will get your answer. Since it's squirrels, you can round to the nearest whole number. So with these percentage problems, you'll want to change it to a percent and add to 1 if it's increasing, subtract from 1 if it's decreasing. All right, your assignment will be the next 2 pages.